Hello everyone, today we're going to have the testing of hypothesis. This resolves the course outcome, apply statistical methods in the analysis of data. The intended learning outcomes are structure engineering decision-making problems as hypothesis test. Test the hypothesis on the mean of a normal distribution using either z-test or the t-test procedure. Test the hypothesis on the variance or standard deviation of a normal distribution. Test the hypothesis on a population proportion. Use p-value approach for making decisions in hypothesis test. Compute power and type 2 error probability. Explain and use the relationship between confidence interval and hypothesis test. What is a statistical hypothesis? A statistical hypothesis is a statement about the parameters of one or more populations. This may also be thought of as a statement about the probability distribution of a random variable. For example, consider air crew escape system. Suppose that we are interested in the burning rate of the solid propellant. Now, the burning rate is a random variable that can be described by a probability distribution. For the burning rate, specifically, we are interested in deciding whether or not the mean burning rate is 50 centimeters per second. Formally, we can write it down as the null hypothesis, mu is equal to 50 centimeters per second. We have to prepare an alternative if this is not true. So that's the alternative hypothesis H1. Mu is not equal to 50 centimeters per second. HO is the null hypothesis. H1 is called the alternative hypothesis. A two-sided alternative hypothesis because of the symbol not equal. This can be written as a one-sided alternative hypothesis, or there are certain other alternative hypotheses like the null hypothesis is equal, mean is equal to 50 centimeters per second against the alternative that the mean is less than 50 centimeters per second. Another alternative hypothesis would be when the mean is equal to 50 centimeters per second and the alternative is mean is greater than 50 centimeters per second. It is important that the hypotheses are always statement about the population or distribution under the study, not a statement about the sample. So take note that this is always about mu, sigma, and p. The null hypothesis mu is equal to 50 centimeters per second against the alternative mu is not equal to 50 centimeters per second. So take note of this as our main concern of our study. So suppose that a sample of n is equal to 10 specimens in tested and that the sample mean burning rate x bar is observed. The sample mean is an estimated of the true population mean, mu. A value of the sample mean x bar that falls close to the hypothesized value of mu equal to 50 centimeters per second does not conflict with the null hypothesis that the true mean is really 50 centimeters per second. On the other hand, a sample mean that is considerably different from 50 centimeters per second is evidence in support of the alternative hypothesis H1. Thus, the sample mean is the test statistic in this case. The sample mean can take on many different values. So for the critical region, um, if we will be considering 48.5 and 51.5 as the range of acceptance region, so we do not reject the hypothesis from 48.5 to 51.5. And then the critical region would be the region outside this acceptance region. So the values in the interval x bar is less than 48.5 and x bar greater than 51.5. So we reject the null hypothesis in favor of the alternative hypothesis. These two sets of value, 48.5 and 51.5, are the critical values. These are the boundaries between the critical region and the acceptance region. There are different errors in the decision for testing of hypothesis. We have type 1 error and type 2 error. Type 1 error is rejecting the null hypothesis H null, H naught, when it is true. For example, the true mean burning rate of the propellant could be equal to 50 centimeters per second. However, for a randomly selected propellant specimens that are tested, we could observe that the value of the test statistic x bar falls into the critical region. We would then reject the null hypothesis in favor of the alternative H1 when in fact H null is really true. A type 2 error occurs when we fail to reject the null hypothesis when it is false. Suppose that a true mean burning rate is different from 50 centimeters per second, yet a sample mean falls in the acceptance region. In this case, we would fail to reject HO when it is false. So we have 4 possible cases. We can have a true hypothesis against a false hypothesis. So if the statement is true and we do not reject it, there's no error. True and you do not reject that, there's no error. If the statement is false and you reject it, there's no error. But if the statement is false but you do not reject it, so you are committing type 2 error. If the statement is true but you reject it, you're committing type 1 error. So let's have some cases. I have the winning combination for the lottery. If you have the winning combination for the lottery, what would be a no error statement or a correct decision statement? You can bet on the number and you actually have the winning combination and win. This is a nice situation to be in. You have the winning combination, so you bet on it and then you win. Another correct decision is you do not bet on the number. And the winning combination is different. So you do not lose any money on betting on a number which would not come out on the lottery. When do we commit type 1 error? Type 1 error is rejecting the hypothesis. So I have the winning combination, but you reject the hypothesis, so did not bet. But the number is indeed the winning combination. So this is an unfortunate situation. You are supposed to have the winning combination, but you did not bet on it. For type 2 error, you fail to reject the null hypothesis. So you agree that you have the winning combination. So what happens is you bet. But you do not have the winning combination, so you lose. So these two cases is okay, making correct decision. Among the two types of error, we do not want this to happen. We do not want to commit type 1 error. This is quite unfortunate that you have the winning combination and you're not going to win. Type 2 error is a little bit acceptable. You bet and lose, so you lose your betting money. Let's try another one. Using an expensive soap kills 99% of the germs. So correct decision, use the soap. And kill the germs. So you use the soap and you kill the germs. Correct decision number 2 is not buying the soap or not using the soap. Well, in fact, it does not kill the germs. So the correct decision is save money on not using an expensive, ineffective soap. So you reject the hypothesis. Well, in fact, it is false. What is type 1 error? Reject the null hypothesis. So we reject the hypothesis that using the soap will kill 99% of the germs. So we reject the hypothesis. So do not use the soap. You do not use the soap, but it was supposed to kill the germs. So, and be infected with a disease. So we don't want this to happen. Failing to reject the null hypothesis when it is false. So the statement is false. The soap will not kill the germs. So, but you do not reject it. So you use the soap. But it did not kill the germs. So for this one, it is good that you use the soap, you buy the expensive soap and kill the germs. For this one, the soap is not effective, so what happens is you did not use the soap and you save money on not using the soap. Type 1 error is rejecting the hypothesis. So we do not agree that it is an effective soap, so you did not use the soap. However, the soap is effective in killing the germs. So the germs, you did not use the soap, so you might be infected with the germs. Type 2 error is failing to reject the null hypothesis when it is false. You use the soap. You agree on using the soap, but it did not kill the germs. So there's nothing bad in trying. However, um, the soap did not really kill the germs. So, but what we want to do is to avoid committing type 1 error of not using the soap, but it is in fact capable of killing the disease. These are the references we can use for these studies.